Hi class, starting this week, we'll discuss correlation and regression. First, we'll review what you learned about these topics in EDPR 8541. The concept correlation is a key to understand the relationship between two variables. Knowledge of this relationship helps us determine how one variable changes concerning the other. To analyze these relationships, statisticians developed measures of bivariate associations. In general, all measures of bivariate relationships focus on two key characteristics of correlation. One is the direction of the relationship, which can be positive, negative, or curvilinear. The other is the strength, which is about the magnitude of the association between the two variables. I will use the Pearson correlation coefficient to illustrate this concept. However, please be aware that there are many different measures assessing bivariate relationships, and your task is to choose the appropriate one based on the measurement scales of the two variables and whether they share a linear relationship. Pearson correlation measures the strength of association between two quantitative variables that have a linear relationship. In other words, both variables, x and y, must be either interval or ratio variables. To check for a linear relationship, use a scatter plot. If you're unsure how to generate a scatter plot, refer to the linked video tutorial. The Pearson correlation coefficient R ranges from -1 to +1. The sign indicates the direction of the relationship. For example, a negative relationship between time spent outdoors and depression level means that more outdoor hours are associated with lower depression. The absolute value of Pearson's R measures the strength of the relationship. When R is close to 0, the relationship is very weak or non-existent. The closer the R value is to 1, the stronger their correlation is. One key property of correlation is that it is symmetric, meaning that the correlation between x and y is the same as between y and x. On this slide, I have a few examples to show you how different relationships appear visually in scatter plots. In scatter plot A, there is a perfect negative relationship because all points lie on a straight line. In scatter plots B and C, both have R equals 0.7, but they appear different due to the swapped positions of x and y. This demonstrates that correlation is symmetrical. When you compare scatter plots D, E with A, B, C, you can tell that the closer data points clustered around the straight line, the stronger the bivariate relationship. The final scatter plot F illustrates a curvilinear relationship, which Pearson's R does not capture well. Since bivariate measures are in most cases based on sample data, it is necessary to test the significance of R. In SPSS, the Pearson's correlation test checks whether R is significantly different from 0. The hypothesis test follows the same 5 steps. Step 1, we state the hypotheses. The null hypothesis is that no correlation exists between x and y. The alternative hypothesis is that there is a significant relationship between them. Set the alpha value in step 2. In step 3, we compute the test statistic and get its p-value. In step 4, the comparison of the p and alpha leads to a decision either to reject or fail to reject the null hypothesis. SPSS typically does not display an exact p-value, but indicates significance at the specified alpha level. Next, I will briefly introduce alternative correlation measures. You can find video tutorials on the slides for further details. Spearman's rule is a non-parametric version of Pearson's R, and it's used for measuring the bivariate relationship between two ordinal variables. Its value is also between -1 and +1, and the interpretation of the value is the same as the way you interpret Pearson's R. Keep in mind that both Pearson's R and Spearman's rule require a linear relationship between the two variables. The only difference is that Pearson's R is used for measuring the relationship between two continuous variables, whereas Spearman's rule is for measuring the relationship between ranked variables. What if the two variables do not have a linear relationship? Then you can use a measure called the eta coefficient. Unlike Pearson's R, eta coefficient is asymmetric, meaning one variable must be identified as the dependent variable. The value of an eta coefficient is between 0 and 1, because in a curved linear relationship, the direction of the relationship may vary over the course. The phi coefficient is another special case of Pearson's R. It's used to measure the relationship between two dichotomous variables. For example, if you want to know how gun control attitude is associated with gender, the phi coefficient is the right choice. The way to interpret the value of a phi coefficient is exactly the same as how you interpret the Pearson's R. Next, we have the Goodman and Kraskov lambda coefficient. It's used to measure the relationship between two nominal variables, x and y, when both variables have more than two values. For example, if you want to examine the association between individuals' racial background and their political party affiliation, the lambda coefficient is the right choice. Again, it's a special case of Pearson's R and follows the same interpretation. The last topic of this video is about the relationship between correlation and causation. In your homework, I always make comments to remind you to avoid phrases or words that imply causation. The reason is simple. Correlation is not causation. If you would like to claim that variable A causes the changes in variable B, three conditions must be met. Number one is about the temporal order, meaning that the cause A must occur before the effect B. Number two, you need to provide evidence to show that the two variables have a statistically significant relationship. And number three, which is the hardest condition to meet, is that other possible explanations must be ruled out. For example, claiming that motivation improves academic performance, you must show that motivation significantly predicts student scores while controlling for rival factors such as self-efficacy and IQ scores. If you had taken a course about research design, you would remember that causality is the concern of internal validity. Internal validity refers to the extent to which a study controls for confounding variables to establish causality. In experimental studies, internal validity is improved by random assignment, in which participants of a study are randomly assigned into different treatment conditions. In observational studies, controlling for extraneous variables is more challenging, making causal claims unlikely. That's why I want you to be very careful not to use wording that claims causal relationships between variables. When designing a study, we also need to be mindful of external validity. External validity is about the generalizability of the findings of a study. Studies with strong external validity offer results that can be generalized to other settings, other people, or over time. Carrying out your study in a more natural setting is a way to improve generalizability across settings. In most cases, researchers are concerned with generalizing findings from their samples to the underlying populations, which is only possible when the sample is randomly selected. If a study relies on convenience or volunteer sampling, it's important to avoid making broad generalizations. Finally, do not confuse random assignment with random selection. Random assignment enhances internal validity and establishes conditions for making causal inferences. Random selection enhances external validity and provide a foundation for improving generalizability. All right. Thank you for watching.